After completing a reaction, the resulting product is usually not pure. Typically, it is present as a crude mixture, containing byproducts and unreacted starting material and reagents. Liquid-liquid extraction is the most common technique for separating a compound from a mixture. This method takes advantage of differences in solubilities in order to selectively separate the components. The sequence of extraction and washing is known as working up a reaction. By using appropriate solvents, the desired product can usually be separated from the unwanted impurities. Remember, we did a mini extraction to remove the DMSO before evaluating the reaction mixture by TLC. An extraction involves the removal of the desired compound from a mixture, and a wash involves the removal of unwanted impurities from the desired compound. In this process, components of a mixture will be distributed between two immiscible solvents. Since these solvents are insoluble in each other, two distinct layers are formed when combined. This is what you would see if you mixed oil and water. Usually water is used as one of the solvents, the aqueous layer. The other is an organic solvent, ideally with a low boiling point, so it is easy to remove after the product has been isolated. How do we know which layer is which? Density. The more dense solvent will be the bottom layer, and the less dense will be the top. Consequently, the aqueous layer is typically, but not always, the bottom layer, and the organic is the top. One solvent that breaks this rule is methylene chloride. It has a density of 1.325 grams per mil, so it will be on the bottom. If you are having trouble determining which layer is which solvent, you can add a drop of either solvent, water or organic solvent, to see which layer it goes to. The different components of the mixture are selectively distributed in one solvent or the other, depending on their different solubilities, or their affinity for one solvent over the other. In most cases, but not all, neutral organic molecules prefer the organic phase, while charged molecules and inorganic salts prefer the aqueous layer. As you go through this workup process, be sure to keep track of the layers and which layer you want to keep. The glassware typically used for this separation is a separatory funnel. A separatory funnel, or SEP funnel, is handy since you can drain out the bottom layer and pour off the top layer. But we won't use a separatory funnel since we are working with small volumes. We will use a screw-capped test tube, which will be more efficient when working with small volumes. Let's see how this technique works as we relate it to the workup step for Unit 1. After synthesis, ideally only the desired benzaldehyde product would be present. In reality, side reactions tend to take place, leading to the presence of side products. Byproducts will also be present. Since reactions do not always go 100% to completion, starting materials and reagents are also present. Let's look at what is in the reaction vial after the synthesis of benzaldehyde from benzyl alcohol. Starting material benzyl alcohol will probably be present, hopefully in small amounts. The solvent DMSO will be present. Hydrobromic acid was a catalyst, so it was regenerated. The product benzaldehyde will be present, and byproduct dimethyl sulfide is present. We need to consider how these compounds distribute themselves between water and an organic solvent such as diethyl ether. Which compounds are soluble in water? Which compounds are soluble in diethyl ether? We make use of these differences in solubility to isolate or extract the desired product. Right away, you can see that there's a problem. Extraction will not isolate benzaldehyde from the starting benzyl alcohol. Their structures and thus solubilities are too similar. This is a disadvantage of the extraction technique. Later this semester, we will learn other separation techniques that will allow us to separate compounds with similar structures. Keep the organic extracts, but discard the aqueous washes. However, wait until the end after you are 100% sure you have product before discarding any layers. How will we do this? Use a screw cap test tube large enough so that it is no more than 3/4 full. You want room to sufficiently mix the solvents by shaking. Using tweezers, remove the spin vane from the reaction vial. Rinse off the spin vane over the vial with 1 ml brine. Brine is saturated aqueous sodium chloride. This will remove any residual reaction mixture on the spin vane. and also increase the volume of the aqueous layer. Transfer the reaction mixture to a screw-capped test tube using a disposable pasture pipette. You want to extract with something the product is soluble in, or is more soluble in than water. We'll use diethyl ether, which is insoluble in water. Rinse the reaction vial with approximately 1 ml diethyl ether and transfer the solvent to the test tube. You will need to mix the two solvents very well, which will increase the contact surface area and cause the distribution of the compounds in the solvents. Compounds will seek out the solvent in which they are more soluble. So we're extracting the product out of the aqueous layer and into the organic layer. Mixing frequently causes pressure to build up inside the test tube, particularly if volatile solvents are used, like diethyl ether, or if you use solvent that can generate gas, like sodium bicarbonate in acidic conditions, and CO2 is released. Cap the test tube and shake vigorously for several seconds. Make sure the cap is on tightly. Carefully unscrew the cap to release any built-up pressure. Repeat the shaking and venting several times. Set the test tube in a clamp stand and remove the cap once the test tube is secure. Let the layers separate. Ideally, 2 layers with a nice clean interface will quickly form. However, things don't always go as planned, and sometimes a thick, cloudy layer, an emulsion, can form between the 2 solvent layers. An emulsion is a colloidal mixture of 2 solvents. This is often caused by impurities that are present or the slight solubility of water in some organic solvents. It can be hard and time-consuming to get rid of an emulsion. The easiest process is sitting and waiting for 2 clear layers to form. If this is taking too long, you can stir and swirl the emulsion. Sometimes just flicking the side of the test tube with your finger will do the trick by encouraging the more dense solvent to fall out of the emulsion. If one of the layers has a greater volume than the other, add more of the lower volume solvent and gently swirl. Sometimes the addition of a little saturated sodium chloride solution will work. Add approximately 1/2 ml and swirl. The sodium chloride increases the ionic strength of the aqueous layer and decreases the solubility of the organic solvent in the water. The salt essentially pushes out the organics from the aqueous layer. Once 2 layers have formed, you need to physically separate the layers. Carefully pipette out the ether layer and place it in a clean vial or flask. Be careful not to remove any aqueous layer when you get to the interface. Since you will be extracting several times, it's better to err on the side of leaving a little ether than removing water. What's left in the test tube is the bottom aqueous layer. To ensure that all of the product has been removed, you want to keep extracting the aqueous layer with diethyl ether. Do this 2 more times using 1 ml diethyl ether each time. After each addition, mix, vent, let separate, and remove the top organic layer. Combine this organic layer with the one previously removed. You are extracting the reaction mixture with diethyl ether 3 times, each time using 1 ml, or 3 times 1 ml. This is all you need to write in the procedure of your final report for the extraction. The product was extracted with diethyl ether, in parentheses, 3 times 1 ml. The extraction technique is a standard operating procedure, so you don't need to include the details of shaking, letting separate, etc. However, since this is a new technique for you, it would be good to write these details in your notebook. Once the extraction is complete and the organic diethyl ether layers have been combined, you want to wash this with approximately 2 ml brine. Transfer the organics into a clean screw cap test tube, then add the brine. Shake, vent, and let the layers separate. This final wash will help to remove small amounts of water still in the ether. Water is slightly soluble in ether, not to a large extent, but there is likely some in the organic layer. Remember that the high ionic content of the brine will decrease the solubility of the water in the ether, which will remove it from the organic layer. Note that diethyl ether has a low boiling point. As you do these extractions and washes, there's a chance that some of the ether will evaporate. If the organic layer is significantly smaller than the aqueous, add a little more ether to the test tube. Now that you have washed the pooled diethyl ether extracts, there's still a chance that residual amounts of water remain in the organic layer. To remove trace amounts of water, we will use a drying agent. anhydrous sodium sulfate, Na2SO4, which will adsorb any water molecules present. This is referred to as drying the organic layer. We will do this by passing the organic layer through a small column of sodium sulfate. The column we will use is a short pasture pipette with approximately 250 to 500 milligrams of anhydrous sodium sulfate, roughly 2/3 of the pipette. This is a granular salt that looks like sodium chloride. To prevent it from falling out the bottom of the pipette, plug the pipette with a small amount of cotton. Use a long pasture pipette to push the cotton into the smaller pipette. If too much cotton is used, it will take a very long time for the organic layer to elute or pass through the column. In addition, if too much water is present, the flow of solvent will stop. Use a piece of folded weighing paper to transfer the sodium sulfate to the pipette. Try not to be as messy as I was. Doing this over a trash can is a good idea. Clamp the drying column onto a stand and pipette the organic layer into the column. Make sure a pre-weighed screw cap vial is underneath the column to collect the product as it elutes. Pipette the organic layer and only the organic layer into the drying column. Once the solvent has been collected, rinse the drying column with approximately 1 ml of diethyl ether to remove any product that has stuck to the surface of the sodium sulfate. To obtain the crude product, remember that some starting material may be present, so it's likely not 100% pure. Evaporate off the diethyl ether under a gentle flow of nitrogen gas. Make sure that the needle is secure in the tubing and that the gas is not turned up too high. Turn on the gas first before placing the needle above the surface of the solvent. Check the flow by carefully feeling the breeze against your forearm. Do not stick yourself. Secure the nitrogen line above the vial. As the solvent is evaporating, evaluate the dilute product solution by TLC. Once the solvent has evaporated, determine the final weight and the percent yield. How do we know all of the solvent is gone? First, know how much product you are expecting. Is the product final weight close to that? Second, dry to constant weight, meaning that you weigh the product in vial, put it back under nitrogen gas for 5 minutes, and weigh it again. If the weight remains constant, this indicates all of the solvent has evaporated. Label the capped vial and leave it on your benchtop. Your instructor will evaluate the remaining product by IR spectroscopy for you. Use the Spectral Database for Organic Compounds, SDBS, to look up IR spectra of pure benzyl alcohol and pure benzaldehyde and compare them to the IR spectrum of your product. Complete the post-lab assignment.